Welcome back. In this video we're going to discuss Hess's law. And if you've watched the video on enthalpy, you understand that when we talk about enthalpy changes, we're really just talking about how heat flows or how energy changes within a chemical reaction. And your next question might be, alright, how do I use enthalpy to solve problems which may show up on my next test or maybe even the AP exam? And I'm going to tell you that the majority of problems you're going to need enthalpy to solve are going to relate to Hess's law. What is Hess's law? Well, this is what Hess's law says. In going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. Now, I'll admit this definition is a little complicated, and without doing an example, it probably makes absolutely no sense to you. So let's just dive into a fairly simple example, and then we'll return to this definition and see if we can make some sense of it. So here is a reaction. We've got nitrogen gas, 1 mole of nitrogen gas plus 2 moles of oxygen gas yields 2 moles of nitrogen dioxide. And we're tasked with finding the enthalpy change of this reaction. Now, without a really expensive lab and these chemicals to actually do the reaction, we're not going to be able to figure this out. We're going to need to be given some additional information. And here is that additional information. We are given 2 more reactions, and we're given the enthalpy changes for those reactions. So in this one right here, we've got some nitrogen gas plus some oxygen gas yields 2 moles of nitrogen monoxide. And here we've got 2 moles of nitrogen monoxide plus 1 mole of oxygen gas yields 2 moles of nitrogen dioxide. Now let's just go ahead and add these reactions. I promise this will get us somewhere, but just bear with me for a few minutes. So when we add reactions together, we're just going to take the reactants from both reactions, put them on the left-hand side, and take the products of both reactions and put them on the right-hand side. So in terms of reactants for this new reaction, we've got nitrogen gas plus, I'm going to drop the state symbols because everything is gas and they're kind of irrelevant. So N2 plus oxygen gas plus 2 nitrogen monoxide plus another O2 from here is going to yield 2 nitrogen monoxide plus 2 nitrogen dioxide. Let's do a little bit of combining. We see that we've got 2 individual moles of oxygen gas here, so we can combine that. So we've got N2 plus 2O2 plus 2NO yields 2NO plus 2 nitrogen dioxide. Now, there's something else interesting here. We've got 2 moles of nitrogen monoxide on the reactant side of the equation, and we've got 2 moles of nitrogen monoxide on the right-hand side of the equation. So nitrogen monoxide sort of exists on the left-hand side, and it exists in exactly the same form on the right-hand side. So it really doesn't do anything in the chemical reaction. It doesn't participate in any chemical changes. So we can just cancel that out. So what we get as our net reaction is we get N2 plus 2O2 is going to yield 2NO2. Aha! This is interesting. This is equal, I wonder how, to the original reaction for which we were trying to find the enthalpy change. So the question is, now that we've found this reaction by adding 2 individual reactions, what is the enthalpy change of this reaction? Well, it sort of makes sense that if we add 2 reactions together, we add their reactants, we add their products, shouldn't we just add their enthalpy changes to get the new enthalpy change? And that's exactly what we're going to do, and that's perfectly valid. So the enthalpy change of this reaction is going to be equal to the enthalpy change of the first reaction, 180 kilojoules, plus the second, so minus 112 kilojoules. And if we do some quick math, that's equal to 68 kilojoules. And so we've solved the problem. The enthalpy change of this reaction is equal to 68 kilojoules. So what have we done here? Well, here we've essentially added some constituent reactions, some steps of a reaction together to form a final reaction, and figured out the enthalpy change of that final reaction by adding together the enthalpy changes of the individual steps. And that is essentially Hess's law. So if we return to the definition, in going from a particular set of reactants, these here, to a particular set of products, these here, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So in this series of steps, we start with the same reactants, we finish with the same products, And so the enthalpy change as a whole of this set of steps, which is just going to be equal to the enthalpy changes added together, is also equal to the enthalpy change of the overall reaction. So we can figure out the enthalpy change of the overall reaction by looking at the enthalpy changes of the individual steps. And here are some steps to solve Hess's law problems. So the first thing you're going to do is you're going to take a look at reactions that you're given, and you're going to add them together in some fashion to find your net reaction. So here we just added them together, added the reactants together, added the products together, and we formed our net reaction. Sometimes we're going to want to flip reactions. So maybe in our net reaction, we have a product, but in one of our steps that shows up as a reactant, we can just flip the reaction and then add it in that way to get the correct reaction which we want. If we do that, we have to reverse the sign of the enthalpy change. So if it's going in one direction and it's positive, and we flip it, the enthalpy change now becomes negative. That's sort of intuitive. And finally, if a reaction is multiplied by an integer, you have to multiply the enthalpy change by that integer. So maybe we had in this reaction, I don't know, 4 moles of nitrogen dioxide and 4 moles of oxygen and 2 moles of nitrogen dioxide. To get the enthalpy change of that reaction, since we multiplied every coefficient by 2, we would have to multiply this enthalpy change by 2 to get the net enthalpy change. And so now let's apply these steps to a problem that's a little more challenging, actually significantly more challenging, and that is to find the enthalpy change for this reaction with some water plus some solid carbon yields carbon monoxide plus some hydrogen gas, given these reactions right here. Alright, so the first thing we're going to do is we're going to try and add these reactions together to get this reaction. And we're going to notice a few things. In this reaction, we have water as a reactant, and over here, we have water as a product. So we're probably going to want to flip this reaction so that we get water on the left-hand side of our net equation. So let's flip this. So we get H2O yields H2. I'm again dropping the state symbols because they're really irrelevant to these kind of calculations. H2 plus 1/2 O2. And remember that when we flip a reaction, we're going to flip the sign of the enthalpy change. So this is now going to become 240 kilojoules. Same thing over here. We see that we've got carbon monoxide as a reactant in this reaction and a product in our net reaction. So we're going to want to flip this to get carbon monoxide as a product. We also see that we only have 1 mole of carbon monoxide as a product over here, but if we flip this, we'll have 2 moles as a product over here. So we want to divide this reaction by 2 so that not only do we get carbon monoxide as a product, we get the correct number of moles, the correct coefficient for carbon monoxide. So if we divide this by 2 and flip it, we're going to get 1C plus 1/2 O2 yields 1CO. And the enthalpy change of this reaction is going to be equal to the negative of this, so negative 221 divided by 2. Negative 221 divided by 2. And I'm just going to punch that in on my calculator right now. Negative 221 divided by 2. You can probably do that in your head. But that is negative 110.5. Alrighty, let's add these reactions together and see if we've manipulated them in the correct way. I'll flip colors to a nice magenta, and we get H2O plus C plus 1/2 O2 yields H2 plus 1/2 O2 plus CO. Yay, we can cancel these 1/2 O2's, and our net reaction just becomes H2O plus carbon yields carbon monoxide plus H2, which I believe, and I'm correct, is the reaction we were looking for. So now we can go ahead and just add these manipulated enthalpy changes to get the enthalpy change of our final reaction. So the enthalpy change overall is equal to 242 minus 110.5, and that's the correct number of significant figures, is 132 kilojoules. 132 kilojoules. So this reaction is endothermic because it absorbs energy. The enthalpy change is positive. And so that's how we solve Hess's law problems. We manipulate the steps we're given to add them to create the final reaction. We also manipulate the enthalpy changes accordingly in the same way, and then we add the constituent enthalpy changes to get the enthalpy change for the final reaction. Thanks for sticking with me, and I'll see you in the next video.